Hello, my name is Aazan. Today, we're going to present a joint work between me and my supervisor, Antoine, Girard, Paolo, and Luca, Greco. It's about the stability of discrete-time switched linear system driven by omega regular switching sequences. So before we introduce our results, so we begin by a motivating example. For instance, we consider a network consisting of 3 discrete-time oscillators, described as the following figure here. So, and the oscillators are communicating together by communication channels. And at each instant, only one communication channel is active and it's selected by a switching signal theta. For instance, if theta equal 1, there will be communication between agents 1 and agent 2. And if theta equal 2, there will be communication between agents 1, 2, and agent 3, and so on for theta equals 3. We consider here in our examples that our oscillators are linear, and the dynamics are given by the following equation. For instance, if we take theta equal 1, there will be communication between oscillator 1 and oscillator 2. We see here that the inputs for 1 and 2 are not non-zero. However, it will be 0 for the agent 3. And if theta equal 2, the communication is between agent 2 and agent 3. And we see here that the input for 2 and 3 is not 0. However, it will be 0 for the oscillator 1. And so on for theta equals 3. So if we consider now x of t to be the synchronization error, which is the error between oscillator 2 and oscillator 1 from a side, and the error between oscillator 3 and oscillator 2 from the other side. So we get a 4-dimensional switched linear system with 3 modes here. And the matrices A is describing the communication channel. So A1 correspond to the channel communication channel 1, and so on for A2 and A3. So our goal is to synchronize the oscillators here, and this, in other words, is to letting this this quantity here go, the x of t here go to 0 at infinity. And however, it's impossible to do that if we keep activating the same communication channel. Therefore, theta cannot be arbitrary here, and hence we impose a fairness constraint on theta that theta cannot keep activating the same communication channels always. And this constraint here can be described as the following LTL formula here, or by the following proposition, this logical proposition here. So this LTL formula here corresponds to a somehow of a omega regular language. So now, generally speaking, if we want to formulate our problem, we consider now a discrete time switched linear system of the following form, where x of t is a continuous state vector and A is a finite set of matrices. So our goal here is to study the stability of these systems here when theta is a omega regular, belong to an omega regular language. And it's known that the omega regular language can be generated by a Buchi automaton. So we don't take here theta to be arbitrary. In fact, theta is generated by a Buchi automaton. Now, if given a finite set of matrices A and a Buchi automaton B, our goal is to provide sufficient and necessary condition for stability of the system AB. So we have seen that theta taken our example is generated by a Buchi automaton. And so what is a Buchi automaton? A Buchi automaton consists of a finite set of states. So here in our case, it's a finite set of states, and linked together by transitions over a specific alphabet. And what's special here is that Q0 here is an initial state and an accepting state. So if we input an infinite word to this Buchi automaton here, the corresponding infinite run, it will correspond to an infinite run. And if this infinite corresponding run will visit Q0 for infinite number of times, we say that this infinite run is accepting. And the set of all words having an accepting run on this automaton here is nothing but the language of this automaton here, of this automaton B here. So we see here, for instance, if we keep activating the channel 1, we see that we don't visit Q0, so for infinite number of times. So we see here that this automaton here can describe perfectly our theta in our example. So this Buchi automaton will be considered in our example. So since we mentioned stability, so it's natural to define notions about stability. So we say that the system AB, given a finite set of matrices a Buchi automaton B, we say that AB is globally attractive and globally uniformly stable if for all theta that belongs to the language of this automaton B, of this Buchi automaton B, we have the trajectories go to 0 at infinity, and our trajectories are bounded for all three. So now, before giving sufficient conditions on stability, we proceed by a Lyapunov approach. So we take V somehow an energy function acting on each state. So we take V to be a function of so V in fact is a function that takes an argument in Q, a vector in the Euclidean space, and output a positive number. So, and what's the thing here is we impose a constraint on V, that is, this V must not increase each time we visit a non-accepting state. However, this function V must decrease each time we visit an accepting state on the Buchi automaton. So this V can be applied directly on the Buchi automaton. And the intuition here is, since that this state is accepting, and therefore this state will be visited infinitely often on the Buchi automaton. So this state will be visited infinitely often, and this equation here will be activated infinitely often, and this equation will lead to the decay of the function p, and therefore v will go to 0 at infinity. So this intuition here, or this approach here, let us build this theorem here. So if we can find a function v that is bounded between the trajectories, and it's not increasing each time we visit a non-accepting state, and it's strictly decreasing each time we visit an accepting state here, given by these conditions here, and rho here can be seen as a contraction coefficient, so between 0 and 1. And so if we can find such a function v here, so we say that the system AB is globally attractive and is globally uniformly stable. And the good thing here is that this function v can be sometimes taken to be quadratic of the following form. And therefore, these equations here can be transformed into a linear matrix inequalities, which can be solved by solving a convex optimization problem. So we'll see, for instance, in our example here. So if we take V to be quadratic of the following form, and we apply V directly on the condition of the theorem directly on the Buchi automaton of theta, so we get a system consisting of 16 linear matrix equalities here. So hopefully we get a solution when rho equal to 0.96. So we get a for function V, each one correspond to a state here. So now if we simulate our work, so if for instance, if we take theta to be 1, the communication channel between agents 1 and agent 2, we see that the agents 1 and agents 2 are well synchronized. However, it's not the case for agents 2 and agents 3. Now, if we take theta to be equal to, so there will be communication channel between agents 2 and agents 3, we see that these agents here are well synchronized. However, it's not the case for agents 1 and agents 2. On the other hand, if we start to mixing between theta equal 1 and theta equal 2, so between channels 1 and communication channel 1 and communication channel 2, so we start visiting, so 1, 2, 1, 2, we start visiting this state here, this state on the Buchi automaton more frequently. And therefore, this equation here will be activated more frequently. And therefore, we get as a function, our function v will decay to 0 at infinity, and therefore we get the stability of the three considered oscillators at the end. Now, since we gave our sufficient condition, we will show that our sufficient conditions are also necessary for a specific class of system. So for stability. So for instance, if we take an arbitrary Buchi automaton B, so, and we focus only on its accepting state. From this accepting state, we construct a labeled graph by its accepting states. So, so this labeled graph here can be seen as a Buchi automaton whose all states are accepting and are initial states. And the transition between states are over words in LQQF here. And LQQF is nothing but the set of all words that lead us from the set Q to the set QF, from the state Q to the state QF, between visiting any state between Q and QF. For instance, if we take LQ1, Q1, it contains the word 1 only. And if we take LQ1, Q2. So LQ1, Q2, it will contains the word 1, the word 2, 2, the word 2, 1, 2, the word 2, 1, 1, 2, and so on. However, the set LQ2, Q1, so this set is empty, in fact. Now, since we defined the set of words LQQF, now if we take a word in this set LQQF, so we define its corresponding product in the set A. So we define this set here LQQF times, and as a set MBF will be the union of all such products here, with P and Q in F here. So now we see that if A consists is a set of A is the set A corresponds to a contains only invertible matrices. We see that the system here, the system AB, taken here, the stability of this system. So if this system is attractive, we say that this label graph here formed by this system here formed by the label graph G and this set here of matrices is stable. So if this system here is a globally attractive, we say that this system here will be also globally attractive. In fact, the attractivity is equivalent. In fact, in the case where A consists only of finite set of invertible matrices. So since we evoked the constraint system, so a constraint system consists of forming labeled graph and a set of matrices here. So we form a constraint system. And now we use a result in a paper of Matthew Philip and its co-authors. So about multinorm. So a multinorm of a constraint system is a set of cardinality of F norms acting on the Euclidean space. And the value of a multinorm can be seen as the least value of gamma such this inequality here holds when P and Q are in F. And another important result in the paper is that when the constraint system is attractive, then it admits a multinorm H of the following form. So this multinorm with value less than 1. So this multinorm here can be seen as a contracting multinorm. So now we are ready to evoke our necessary condition for stability. So in the case when the matrices in A are invertible, and if the system AB is globally uniform, stable, and globally attractive, then we see that this constraint system here, the formed constraint system here, will be also attractive, and therefore there exists a multinorm for the following form here. Now, if we use the following multinorm, we use the following multinorm to construct our Lyapunov function. So the Lyapunov function would be seen like this. So VQX will be of this form, and the norm of QF, in fact, is from this multinorm here. And this Lyapunov function can be seen that it can be act directly on the system AB here, considered AB. So it can be serve as a energy function for the system AB. So to end up, we have successfully established sufficient condition for stability and necessary condition for stability for a specific class of systems. And however, can we always obtain an upper bound on the convergence rate of the trajectories? And what about this tightness, especially if the considered Buchi automaton is non-deterministic? And we have seen in our example that considered linear matrix inequalities were feasible. However, it's not the case generally. So what to do in that case? So finally, I would like to thank you for your attention.